Hello and welcome to the video. Please excuse ahead of time any mistakes or utterances that I make that don't quite make a whole lot of sense. I'm trying to put the video together pretty quickly for you guys. Anyway, welcome to topic 3. We're actually going to be talking about topic 3 here. And in particular, we're going to be looking at part 3 of this, the basics of probability. So let's go back to this big picture that you've seen before. So far we've discussed the first two steps of this big picture. The first one is producing data. That deals with how we obtain data and what considerations affect the data production process. And the second step is the exploratory data analysis, which is the set of tools that will help us to get a very initial feel for the data, exposing their features using graphs and numbers. And so we've already seen that before. Remember that our eventual goal in this course is what we call inference. That's step 4. And that's where we draw reliable conclusions about the population based on what we've discovered in our sample. However, in order to really understand how inference works, we first need to talk about probability. Probability is the underlying foundation for the methods of statistical inference. So let's use a quick example about the death penalty to try to get at that. So let's suppose we're interested in estimating the percentage of U.S. adults who favor the death penalty. In order to do that, we choose a random sample of 1,200 adults, and we ask their opinion. Do they either favor or oppose the death penalty? And in our sample, we find that 744, or approximately 62%, are in favor. So the question becomes, can we conclude that 62% of the population, not the sample, but the population, favors the death penalty? So another thing that one thing we need to take into account here is that this was just one sample. Another sample could have given us a completely different result. However, our sample is random, so the uncertainty is due to chance, not to problems with how we got the sample in the first place. And we can use probability to describe the likelihood that our sample is within a desired level of accuracy. So, for example, we can ask a question like this. How likely is it that our sample is no more than 5% from the true percent of adults who support the death penalty? That's the kind of question we'll be able to answer with probability. We need to keep in mind, however, that probability is not always intuitive, and our intuition will not always serve us well. There's a couple of classic examples that help to illustrate this non-intuitiveness about probability. The first one is called the let's make a deal paradox, and the second one is called the birthday problem. The let's make a deal paradox was named after the game show from the 1960s with the same name. And the idea is this. You have 3 doors that are closed. There's a car behind one door and a goat behind the other 2, the goat being the booby prize. You as the contestant gets to choose one of the doors. However, instead of revealing what's behind the door that you chose, the host of the game reveals one of the other 2 unchosen doors as having a goat. You are then given the opportunity either to stay with the door that you originally chose or to switch to the other door. And the question becomes, what should the contestant do? What do you think? You can actually play this game at the following URL. If you want to pause the video here and go to this particular web address and play the game, you can do so. I'd encourage you not to uncover the explanation because we have one here, but there is an alternate explanation on that website. So feel free to pause and come back if you need to. Well, here are the results. It turns out that probability speaking, you should always switch if you want to increase the probability of winning the car. So in order to do that, we're going to go over to a video explanation so you can see why this is true.
Initially, when you're asked to choose a door, each one of the 3 doors is equally likely to have the prize behind it with probability 1/3. Let's say you choose door A. Now let's divide the 3 doors into 2 groups. There is a probability of 1/3 that the prize is behind the door that you chose, A, and a probability of 2/3 that the prize is behind one of the other unchosen doors, B or C. Say that now the host is revealing door C, which has no prize behind it. You now have the choice between staying with the door A, which you initially chose, or switching to door B. Now that door C has been revealed, there is zero chance that it hides the prize, and therefore the entire probability of 2/3 that was equally divided between doors B and C before is now all attached to door B. Note that there is still 1/3 chance that the prize is behind door A, but there is 2/3 chance that the prize is behind door B, and therefore it is better to switch.
So that's our first explanation of why the let's make a deal problem doesn't work. There are others on the web if you are interested in reading about them. The second example of why probability is not intuitive is the birthday problem. So here's the scenario. You're at a party with 59 other people for a total of 60, including you. The question is, what are the chances, or what's the probability, that at least 2 of the 60 guests share the same birthday? Meaning they're born on the same day of the year, but not necessarily the same year. And for the purposes of keeping the calculation simple, we would ignore leap years. So what is your guess? What is the probability? Is it less than 10%? Is it about 1 out of 6, or 17%? Is it about 50%? How about 75 to 95%? And our last choice, greater than 99%. So think about that. Which one of these would you choose if you were at a party with 60 people? Well, it turns out that the answer is 99.4%, which is highly likely. And that's not always intuitive to people. Actually, the explanation for this is a little bit beyond this course. However, it's here to illustrate the idea that probability is not always an intuitive, straightforward subject. Just to make sure we understand that, these two problems, the birthday problem and the let's make a deal problem, are considered a little harder on the probability side. Unfortunately, we can do a lot of what we need in this course with much easier concepts. So let's dig into that a little bit. Let's start with the question, what is probability? Well, probability is a mathematical description of randomness and uncertainty. It is a way to measure or to quantify that uncertainty. Another way to think about probability is that it gives us the way to talk about the word chance. So we could say, what is the chance it will rain tomorrow? Or what is the chance a stock will go up in price? In other ways, we can also describe this idea of chance as likelihood. What is the likelihood that I will win the lottery? Or the likelihood that I will live past the age 70. Some of the chances here are quite good, so the probability would be high. For others, they're not as good, so the probability would be quite low. For example, it's very unlikely that I'm going to win the big jackpot in a lottery. So let's talk a little bit about notation. We often talk about events in probability, so we'll let the letter A stand for the event that something may or may not happen, and then we'll say that the probability that A happens is denoted by P parenthesis A close parenthesis. We can often use letters to describe these events, or we can use short phrases to do so as well. So for example, this first subdot is indicating the probability of winning the lottery. Or this third one here is the probability that a stock rises. Just keep in mind the probability of an event tells us how likely it is that the event will occur. In terms of the values that probability can take on, all probability values are between 0 and 1, inclusive, which basically corresponds to the probability of something happening. Could be 0%, it could be 100%, or it could be somewhere in between. The probability of A equals 0 means that that event is impossible. There's a 0% likelihood that it will happen. On the other side of the spectrum, the probability of an event being 1 means that that event always happens. But typically, the probability of an event is somewhere between 0 and 1. We say the chance that event A will occur is between 0 and 100%. And in mathematical notation, we can use something like this. We could say P of A is somewhere between 0 over here on the left and 1 over here on the right. So that's a little bit about notation and values. We have some rules that can come in handy. One of them is called the complement rule. If we let A be an event, we can report that the probability of A not occurring. And this is called the complement of A and is sometimes denoted A superscript C. In probability notation, we can say the probability that A does not happen, or not A, is equal to the probability of A complement, and this is 1 minus the probability that A does happen. So there is a relationship between the probability that A happens and the probability that A does not happen. Another way to think about this relationship is in this form. The probability of A happening plus the probability of A not happening is equal to 1. So either it happens or it doesn't. Those two probabilities added together give me a total of 1. Now there's a couple of ways to determine probability. One of them is taking a theoretical or classical approach, and the other one is taking an empirical or observational approach. The classical approach or the theoretical approach can be illustrated with a few examples. If you take a coin and you flip it, and we let H be the event that a fair coin lands on heads. By the way, a fair coin means that it's equally likely to land on heads as it is to land on tails. Then the probability of landing on the heads is exactly 0.5. This is a theoretical probability that's based on nothing other than the fact that we know that it's equally likely for either of those two events to occur, heads or tails. Another example is the rolling the 6-sided dice with numbers 1 through 6 on it. The probability of getting a 5, which we have over here on the left, is the probability that the die lands on the 5 like it is showing right here. And this is exactly 1 out of 6, or about 0.167. This is again under the assumption that this is a fair die, meaning that all the numbers 1 through 6 have an equal chance of landing on that particular number. And then finally we have another example of a spinner with various colored slices on the spinner. And we could say the probability of spinning this and it coming up red is equal to, and if we look at this spinner here, we can see that there's a total of 8 slices and 2 of them are red. So the probability is 2 out of 8, or 1/4, which is equal to 0.25. So there's a 0.25 probability that if you spin this spinner, it's going to land on red. On the other hand, the probability that it lands on blue is 4 out of 8 because there are 1, 2, 3, 4 slices that are equal to blue. This is all relatively straightforward. I think most people can follow this without too much of a problem. Here's an example. Let's suppose you have 38 employees in your company who are eligible for a monthly drawing to be the employee of the month or for some prize based on performance. So let's take the probability P that a given person in the pool is chosen. This of course is going to be 1 out of 38. If each person has one of their name entered once into the hat, so to speak, and a random name is chosen out of the hat, then each given person has a probability of 0.0263. We can also express that in terms of percentages. This is about a 2.63% chance of being chosen. Now what's key here is that each person is equally likely to be chosen. In other words, all 38 names are thrown into that hat, it's mixed around, and no one person has an advantage over another. But going back to this idea of classical versus empirical, what would happen if you flipped a coin exactly 100 times? Would you expect the probability of a head landing to be exactly 0.5? In other words, would you expect that exactly 50 times that coin would land on the head? Probably not, right? Because when you run a trial like this, what they call a trial, there's probably going to be a little bit of variation away from what we would expect. Another interesting question to ask is, how would you know if the coin was not fair? That is, how would you know that the coin was not equally likely to land on heads as it is on tails? Classical probability methods can't answer this for us. It just tells us basically if you have a fair coin what the probability is. The only way to actually answer this kind of question is to do so with experimentation, with observational studies. And so let's transition to that now. We'll talk first about this idea of relative frequency. If we toss a coin or roll a die or spin a spinner many times, you'll hardly ever get the exact theoretical probabilities that you would expect. When we run a simulation, or when we use a random sample and record the results, we're using what we call empirical probability. This is often what we call relative frequency. And sometimes people define this in this way. So to estimate the probability of an event A happening, we're going to repeat a random experiment many times, and then we're going to count how often A happens. So we can define the relative frequency of event A to be the number of times that A occurs divided by the total number of repetitions. It's pretty straightforward. Let's take a look at an example. Suppose as a manager you're interested in morning habits of your employees. You're trying to get them to be more efficient, let's say. So you survey employees over several typical work days to find out if they ate breakfast, call that event B, before they arrived at work. Let's say you took 460 surveys, and 253 of those indicated that they ate breakfast before they went to work. So then if you were to put all 460 of these surveys into a hat, so to speak, and randomly pull one, then the probability of B happening, that they ate breakfast, would be 253 out of 460, or 0.55. You could possibly infer that there's about a 55% probability that your employees eat breakfast before they arrive at work on a given day. Now, that may or may not be totally accurate, but in terms of just running an experiment, so to speak, this is how you could talk about probabilities in a scenario like this. Now, what's important here is to understand that the larger the number of repetitions that you have, the better off you are in terms of estimating what the theoretical probability is. So the relative frequency of an event will approach the theoretical probability of that event as the number of repetitions increases. This is called the law of large numbers. The basic principle is that the actual or true probability of an event A is estimated by the relative frequency in a long series of trials. So if you were to flip a coin many times, hundreds and hundreds of times, the more you do that, the more likely it is that the percentage of those coins that lands on heads will get to 50%. Let's do another example. A ball is drawn randomly from a jar that contains 6 red balls, 9 white balls, and 4 yellow balls. Let's find the probability of drawing a red ball. So this is a lot like some of the homework problems that you're likely to see online. So to answer this question, we're trying to find the probability of drawing a red ball. So in terms of relative frequency, we're looking at the number of times that that event can happen. It can happen 6 times because there's 6 red balls in the jar. However, the total number of possibilities are 19 because we have 6 plus 9 plus 4 is 19. So in terms of relative frequency, the probability of pulling a red ball is 6 out of 19, or 0.316. Keep in mind you always got to figure out what that total is, as well as the total possible number of times the event in question can happen. Here's another example. In a study of brand recognition, 978 customers knew of Campbell's Soup, and 16 did not. We want to use these results to estimate the probability that a randomly selected consumer will recognize Campbell's Soup. So here's the idea. We have 978 who recognize Campbell's Soup. That's the probability that we're looking for. And there are 978 ways for this to happen in this particular example. However, we also have 16 that did not know about Campbell's soup. And that therefore gives us a total of 994 consumers. We get that from adding these two numbers here together, 978 and 16. Therefore, the probability of somebody recognizing Campbell's soup would be the total number of times that that event can happen divided by the total number of occurrences or trials, or 0.984. Third example of a spinner. Here's a spinner with evenly spaced tiles. What's the probability of getting either a 1 or an 8? Notice that on the spinner, each of the tiles or each of the spaces is unique, and we're looking for the probability of either a 1 or an 8 coming up. Now, there are actually two different ways that this event can happen, because it could land on a 1 or it could land on an 8. So we have two different ways that this event could happen. On the other hand, we have a total of 12 spaces or tiles on the spinner, so our probability is 2 out of 12, 1 out of 6, which is 0.167. Here's another example, and please excuse the typo up here. A store gathers some demographic information from their customers, and the following chart summarizes the age-related information they collected. So here you see ages over here in this column, and the number of customers who are in that category over here in this column. Okay, so what is the probability that a customer is at least 20 years old, but no older than 60? Let's call this event A. So, let's take a look. There are a total of 100 plus 94 plus 68 plus 78, or 340 people who are at least 20, starting here, but no older than 60. So these four numbers right here are coming from 100, 94, 68, and 78. So right in here is all of the possible ways here that this particular event, being between 20 and 60, could happen. On the other hand, there are a total of 500 customers in the batch. So if you were to add up all of these numbers right here on the left side, you would get a total of 500. So if you were to throw all of these customers, so to speak, into a big bag, jumble them around and randomly select one of them, then the probability that a person would be between 20 and 60, which we call event A, is 340 over 500, or 0.68. Okay, here's another example. Suppose a test was given to a group of students. The grades and gender are summarized below in the table, right over here. We take one student, choose them at random from those who took the test, and we want to find the probability that the student got an A, given that they are male. So given that they are male is going to restrict the total number in the denominator that we're going to use. So let's take a look at this. We want to find the probability that a student got an A given that they are male. Now what we need to keep in mind here is that the total number of students that we're going to use is not 67. The total here is 33 because we're given the fact that we're dealing only with males. So this row right here is the only one we care about. So we have 33 males, that's our denominator. And now I want to know what is the probability that they got an A. Well, you can see here in the table that there are 12 men who got A's, and so therefore the probability that a student got an A, given that they were a male, is going to be this 12 divided by this 33, or 0.364. So there you have it, a bunch of examples and a quick introduction to probability that you might find useful for topic 3 here. I hope you found it useful. Here's some references if you want to go look up some of this stuff. Most of what I'm taking is, of course, from the Acrobatique, or from OLI, open source materials. All right, that's it. I hope the video was a little bit useful. This is the first one that I've done of this type, so we'll see if we have time to make more of them in the future.